Yeah, now let's play with my simulator and check if this is really working and where are the advantages and disadvantages. Okay, I start WinDFC# and show you where you can find this controller type. First, I set the actuator. So I make a restart of WinDFC# to delete all change values to come to default values. First, I switch the hardware simulator to our process, PT1, 0.4, 1 second, 100 millisecond. I calculate the A1 and B1, and you see the same values we have ahead in our paper. I first want to show you the ideal version. PT1 in ideal version is really theoretical application because no real process has a PT1 characteristic without any delay. So rather theoretical, but we start with simple PT1 model and look what happens. Okay. Second, I need some controllers. So I go into the controller design, switch to ideal PT1, same process, 1 second, 100 millisecond, controller design, OK, and copy. So all controllers now are designed, and I can start my simulator. First, I check the sampling time. If this doesn't fit to hardware simulator, can imagine that nothing can work properly. The PFCs are only visible if you click on advanced view. Then some more fields are open, and then you can see some more things. Just simple view. I have deleted some components not to confuse too much. Okay, advanced view. Then you see here there is an additional PFC and deadbeat by box which can be selected. Okay, first I start with a unit step function and PI controller. A PI with a PT1 is also should work. Don't forget to click the algorithm also to ideal. If we have designed an ideal and we have run in the hardware simulator an ideal, of course, then this algorithm should also be clicked to ideal version. That means without any delay. I start the PID response, and we see the following result. I shift it a little bit up and make this a little bit smaller that you can see the axis. So the PI has an overshoot and then small decreasing. So the final value 1 is reached after 2 seconds. The overshoot can be influenced by the wind up effect. So I try to use a PI with anti-wind up function. If you want to restart it, please note that the hardware simulator can be initialized by this button. If I start this, you see there is a real wind up effect, but the anti-wind up mechanism has the disadvantage that we have now a slow creeping from bottom to up. So a PI is not really a good solution. I want to show you the deadbeat version. First, I check the code by using by deactivating the limiter. If there is a limitation, you know deadbeat behavior is bad, but if I want to check the code, then I use this without any limitation. Then I have an ideal deadbeat, and of course an ideal deadbeat should be ready after one step. So this code is running. Deadbeat new +1 also should be ready after 2 steps. If you see this code, then you see, okay, this is ideal deadbeat. Both are working. Note, don't try the orientation controller. In the degree of 1, ideal version is not working properly, so the orientation controller can show his advantages starting with degree of 2. Forget it at this time. What happens if I delete the last curves and go back to a 10 volt limiter? The deadbeat controller then should behave in a different way. So I run the deadbeat controller now with limiter, and then you see the behavior is nearly identical to the PI. The deadbeat new +1 also is limited, and the result is the overshoot is a little bit smaller, but there is an overshoot and is more creeping to the final value. Now I show you the presented predictive controller for the PT1. So I activate this, but here all controllers of chapter 9.7 are realized. I have to open the parameter page. This is a new page for all parameters, so don't be confused. I will explain all these buttons and fields for all different controller types. This is just PT1 is selected, the model is also set, copied from the designer. We have no delay, 1 second time constant, 0.4K. This is the PFC degree of 1 I have presented in the paper just before, and now I want to check if this is really running. I go back to the curve, say run, initialize the process and run this controller, and you see this orange curve, and as I have told you, this orange curve stops exactly at 1, has no overshoot, undershoot, and then ends up exactly in the final value. I delete all other curves and redraw the last curve with this button, draw again. Then you see, okay, these are exactly 3 steps, and then we end up with my final value 1. If I go to the numbers, you see exactly these are the values we have calculated by hand, and we reach the final value exactly after 300 milliseconds after 3 steps. Okay. Yes, I think I should now go a step further to add a delay. PT1 without a delay is not realistic, so I think we add now a delay, or we switch to the real version and check what happens in this case. But I have to explain a little bit what I can do in my predictive controllers if there is a delay in the process. So I go back to the paper and talk with you with the next delayed model. Very general solution is a Smith predictor. If there is a delay, if process has a delay of 1 sampling time, 2 sampling times, up to any sampling time, so this is a value d times t sub o, then use Smith predictor. That is the name, official name, predictor, official name of the trick I want to introduce. If you have a model-based predictive controllers, then this is very easy to add a delay. The real algorithm, note what this is. A real algorithm was an artificial delay of the controller. In this case, the D is 1. So this is, if I switch to ideal version, we add a delay of 1 sampling time to the process, and then we are independent of calculation and conversion times in real situations. Yeah, but note in WinDF, in my simulator, this real and ideal algorithm is automatically switched. We have no change of the D value. There is no change of D value necessary. It's automatically done if you click between ideal and real. Ideal and real. So automatically here, if I click this, D is 0, and automatically this is D is 1. Yeah, if you have radio buttons to do this. So just note that the controller and the hardware and the designer all are switched to the same radio button, ideal or real. Yeah, what is this predictor? I show this in supplement chapter C 9.11 in my paper. So I open the paper to this page. The trick is that, yeah, if we have the process and the process has a delay, that we have a model where we can switch off the delay. Yeah, if we have identified the process and say, okay, this is a PT1 with a delay, then we have the PT1 parameters and can calculate output values without delay. So the main trick is we control not the process with delay, but we control the model without delay. This goes very fast, and put the controller output values to the delayed process. Yeah, the only way what we have to do is if there are differences between process and model, and in real life, of course, there are all differences, or if there are disturbances which are not covered with the model, then of course X and XM are different. And then if I have no feedback here, we have a open loop control, because we have no real feedback of the signal. So the trick is that we control here in our equation. Look for this. This is the equation for the PT1 modified deadbeat. We use the undelayed XM, but we add the real output of my process and subtract the delayed model output. Of course, if you have a model, then of course our computer can calculate a delayed model output. Just put the values of XM into a shift register and read out the delayed values. That's not a real problem. If model and process fit together, then this and this are both identical values, and this is sum is 0. Yeah, and then we have a good controller. If there are disturbances in the process, then there is a difference, and then we have a real influence to our control loop, and the controller can correct and can compensate the disturbance. Yeah. Okay. Yeah. In chapter 9.11. In chapter 9.11, I just copied the picture out of Wikipedia, German Wikipedia, sorry for the German words. This is a controller, our predictive controller, or any controller, could be any controller. And this is our delayed, Todzeit means the process has a delay. Here, this is a delay operator. This is an undelayed process. And so this is our delayed process, maybe with disturbance. Okay, this works if you have a delay-free model, GS. GS is undelayed, so GS is an undelayed model, and now the controller works with the output of the undelayed model. Okay, without this is an open loop control. We have no feedback. Yeah? If this is totally different, no idea. We produce here controller output values which are absolutely uninfluenced by the real output. So this is not good. So the next step of the Smith predictor is we want to have the real feedback of our process, but then you have X and XP, and this is of course double feedback. That is not good. So we have to subtract the predicted delayed output by our model. This is an undelayed model. Now we add a delay. So this is the predicted, the modeled process output, and if this fit together, we have exact good parameters and good delay numbers here, then these both signals are 0, and this is also 0, nothing comes back. If there is influence of disturbance, then of course you get a correction signal, and the controller can react on disturbances or any other things. If you look, what we do is very simple. We replace X now with original X, but we add the model output undelayed, and we subtract the model output delayed to compensate the delayed process output. So in any controller design, if you replace the measured signal with this and you have a good model, then you can react on any good on any delayed model. I show you this in our situation. First with the delay 1 of a real algorithm, and then I add a delay to the process and show you what happens then. So we go back to the simulator. Okay, first in my hardware simulator now I switch to real, and so internally D is 1 set to D1. Then I of course has to adapt the design of the controller to a real mode, say controller design, say OK and copy and shift it away. And finally I have now my controller box. In the parameters now I have to click to a real algorithm and check what happens with now our controllers. I make a restart with the PI controller. Now the PI controller has no Smith predictor, is react on the design has now added the delayed phase, the phase of the delay, and so the signal is of course here you see the delay, one sampling time delay, and after one delay the output starts. So you see the blue curve was a undelayed modified deadbeat, and this is a PI controller with a small overshoot. If we try to check is this overshoot caused by a wind up, we just play with the anti-wind up controller and you see, okay, yes, there was a wind up effect, but the anti-wind up mechanism is not really an improvement. So I think I should delete this last curve and forget it. Deadbeat controller and deadbeat nu+1 doesn't have also problems. They are limited, and with the delay the behavior is worse. As you see, with limitation doesn't work. If we want to check the code of the deadbeat controller, deactivate the limiter and check if then the code works correctly. You see, if I do this, the deadbeat has one delay and need one step to reach the final value. So the Greek curve is really the response of a delayed original deadbeat controller, and you can forget it. Yeah, that's not good. So I delete the ideal deadbeat controller because real life is not ideal. I delete the deadbeat controller with limited controller output. I reactivate the limiter again and show you now the orientation controller now should work without delay. In ideal mode it doesn't work, but here you see okay, no overshoot, slow creeping to the final value. It's really not good. Yeah, an orientation controller in degree 1 it's also not optimal, forget it. Yeah. So I delete the last curve and show you now what happens with my modified deadbeat version with delay. What happens? You see we get exactly the same result like before. With the blue curve was undelayed, here we have a delay just exactly the same but one step later, and the no overshoot, no undershoot, no creeping. So you see this model-based, we can say model-based controller with prediction has no problem with any delay. I can increase the difficulty by changing now the delay to other values. So I reopen the hardware simulator, and here in the hardware simulator we can add now any number of delay of my hardware. So I add now, I think 500 millisecond delay. If I do this, yeah, then I have a delay of 1 because the real version is used, plus 5. So we have 600 millisecond delay in our loop. If we want to see the PI controller, what the PI controller can do with this, I had to add here a delay of 500 millisecond. Sorry, this must be a second, 0.5. There's a controller design and send these values to the controller box. Let's check what happens now with my PI controller. In this case, we run it and start it, and you see, yeah, 600 millisecond happens nothing, and then slowly the PI goes up, and yeah, we want to see if the controller is working. Again, I run this, start, and now we have 5 seconds. You see, okay, with this delay, this controller is rather slow. Caused by the negative phase of the delay, the gain must be reduced, and the PI controller then has to wait rather long. What happens with the PFC? I have to go into this box. In the model, the Smith predictor has to be changed to the D value of my process. The ideal real version is automatically added, so you just click here the additional delay of the process, and now I hope this works. Let's check. Sometimes the program also has problems, but you see here you get exactly the same curve like before, but shifted just with 0.5 seconds. But then the mechanism is the same, and you are quickly at the end. So with this, you see, with any delay, if you know the delay, this is good. If, of course, your delay is different, your delay of the model is different to the delay of the process, that's not good. Yeah, please note, yeah, if I change to a different number here, look what happens. You will not be happy if you see this. If this doesn't fit, and that is important, you should know this, then of course the controller works not really good. Yeah, so very important is your model identification. If the model identification is not good and doesn't fit to your real delay, then you see this controller cannot work properly. So far, last word is what happens with the disturbance behavior. We have not talked about this. I have to check this. So I go back to undelayed model, real version. Yeah. Next demonstration is I deactivate the delay. In the hardware simulator, I go back to 0. I stay at real version. Then in my design, this should be also changed. Controller design, OK, and copy. So I have the old controllers back. And in my system, I should delete all curves and switch the 1 volt step now to a disturbance input and check what happens now with my PI controller. We expect that the PI controller can compensate this disturbance properly. So you see the following curve. I look for a range of 5 seconds. So there is a maximum point. The dead beat controller also should work properly. Is, I think, a little bit faster. The overshoot is smaller. And note that I have also reduced this delay to 0. That is a good button because any change here is mostly automatically sent to the controller, but this button forced all changes sent to the controllers. Run, init process, start, and then you see what happens. The beginning is the same, but there is really a final value which is not 0, so there is a control error of my very fast, very good reference behavior controller. The disturbance behavior is not optimal. You can not remove the disturbance, but the disturbance error here is small. Note I add a 1 volt signal to the process and the output is 0.04, this is 40 millivolt. Sometimes, depending on the specification of your process, this is acceptable. If not, wait for the next chapter. There is a possibility to add a correction for this. Yeah, but this comes later. Yeah, so I think I stop here and continue now with a second order model based predictive controller, because the first order model is good to show, simple to calculate, but very seldom you can really find a process which fits to a PT1. Okay, let's look for M is 2 in my paper.